always come on such occasions to reflect about the past, and that is amazing. In almost any area of science, if one looks back 60 years, one is simply astonished by how much we have learned in the last 10, 20, or 60 years. In the area of physics which I work, in basic science, the accomplishments have been enormous. We have, for example, we've discovered and understood what we think are the basic building blocks of all the matter that has ever been observed, of all the atoms that build the molecules that build us. And we understand the forces, the four forces of nature that seem to govern all phenomena. We have understood the structure of matter, not just as Democritus told us a few thousand years ago, that matter is made of atoms, but in this last century, we have understood the structure of atoms, and within the last 60 years, the complete structure of the nucleus that makes up the core of atoms. We've understood that atoms have a very small point-like nucleus surrounded by electrons, and now we understand that the nucleus is made ultimately of quarks. All matter that we've ever observed anywhere in the world and indirectly throughout the universe seems to be made, except for one exception we'll come to later, out of quarks and electrons and their partners, other kinds of quarks and electrons that we can only make with particle accelerators. And we've understood the four forces of nature that act on all these particles and from which all of the, ultimately, in a reductionist sense, all the physical phenomena we believe can be explained. These are, of course, the force of gravity, which was understood to Newton and perfected in the last century by Einstein, and the three forces that act within the atom, the force of electricity and magnetism, holds the electrons in place around the atom and explains atomic structure, chemistry, or biology, as well as the two forces that act within the nucleus, very short distances, and so far haven't had much application except in nuclear reactions with good and bad uses. These are the strong nuclear force that holds the quarks together forever inside the nucleus, and the weak nuclear force that changes quarks, one kind of quark into another, and is responsible for radioactivity in the transmutation of elements. We have completed this theory. It is more or less complete at the level of the atom and the nucleus, and it is an amazing end to a story of 2,000 years since Democritus. We've also, just in the last 100 years, mapped out the entire universe, almost from its beginning, and reconstructed almost all of its history. We think back to the first microseconds after the Big Bang. This pictures the history of the universe from the Big Bang, period of rapid, accelerated expansion we call inflation. The universe then settled down and continues to expand at almost a constant rate. And we have more or less understood the complete history of our universe, whose age we know now with a precision of better than 1%. Our universe is 13.7 billion years old, and most of its history is well understood. How galaxies, planets formed from the early state of the universe. And finally, among the rest, I've given just 3 examples of the progress in the last 60 years, we have achieved exquisite understanding and control of matter in all of its different and fascinating phases. kinds of ways matter can manifest itself. And we are now extending this control down to the scale of atoms, whereby we can manipulate atoms themselves and create new kinds of matter with marvelous properties. Some of that we heard in the last lecture. However, I don't want to dwell on the past. I always say that the most important product of knowledge is ignorance. And by that, of course, I don't mean the kind of ignorance that leads to bigotry and to racism and to war, but informed ignorance. Ignorance that produces new questions that can be answered by observation, by experiment, or by theory. You have to know a lot to be able to ask good questions. And it is the story of science that the more we understand, the more questions we realize are yet to be understood. And there are many kinds of questions that we children ask, but we tell them, that's not a good question, or go ask somebody else. We're not ready to ask that question. We don't know enough to be intelligently ignorant. So today, actually, even after these marvelous advances in basic physics, there's an incredible set of wonderful questions, much more interesting than the questions that were asked when I was a graduate student, that we've only learned to ask intelligently because of our great advances in knowledge. So I'm going to discuss today the questions. This talk originated in a talk I gave at the celebration of the 25th anniversary of the Institute for Theoretical Physics that I direct in Santa Barbara, and I ended that conference with a talk which outlined 25 questions that might guide physics for the next 25 years. Well, I'm going to reduce that to fewer in view of the limited time. And these questions deal with physics. Physics is a very broad science. It hasn't split into this kind of physics, that kind of physics. The programs that we run at my institute, where about 1,000 physicists over each year come together to participate in collaboration and research in theoretical physics, discuss everything from cosmology to astrophysics to condensed matter physics, an enormous field about which I will say nothing today. It covers all of ordinary matter, and at the moment is trying to construct marvelous new kinds of matter that exhibit superconductivity at room temperature, to construct new kinds of strange quantum matter that should be the basis of quantum computing. Wonderful field. Particle physics, the study of elementary particles and the basic interactions of nature. String theory. Biophysics. We now have a program on the physics of climate change. Physicists do a lot of things. I say that when I'm forced to define what is physics, I say physics is what physicists do. And physicists are an ambitious and arrogant lot, and they feel they can do anything. So they do things like, nowadays, more and more biology, and I'll say a word about theoretical biology. 15, not 25. I'll start with the first and basic question, the origin of the universe. How did the universe begin? I said a word about the history of the universe, but this is as far as we can look back and see what the universe looked like in the past. It takes light some time to reach us, so we can look back. We look at light that is taken, that has traveled a long way, then we're looking back into the past. And by looking, using radio waves, we can see a picture of what the universe looked like 13.5 billion years ago. It's actually a very homogeneous picture. These little variations in color reflect changes in the density of the universe, 1 part in 10,000. The universe is extraordinarily homogeneous and boring, and more or less astrophysicists have a very good quality